Hey, I'm going to use education to predict wage, and I have the data here. I'm going to upload this file with the slide and education and wage pair data, and there are 2,244. The first line was just label, so there are 2,244, and just to see. Oh, there is someone who have zero education. It can be an error, but I'm not sure. So there are two persons, two people who have zero educations. Anyhow, let's do the same thing. Data analysis, and regression here. Okay, and Y range. Y is wage. Y range, and X range is education. So I'm going to predict Y using X. So Y is wage, X is education. And let me just try confidence level at 99%, just for fun. And line fit, and okay, let's see. Okay, right, you get similar set of tables, and have a look. Let's look at the graph. This is the yellow, excuse me, the blue is the let me point. Blue is the observations. There are a lot, more than 2,000, so it's impossible to show all the. So here I changed it to marker, none. So okay, the blue dots are observations. For example, there are two. Actually, it looks like one, but actually there are two. There are two observations who have the same education and earning similar wages. And there are someone who is making a lot, maybe the maximum possible, at 9 years of schooling. 9 years, okay. And 12 years of schooling implies high school graduation. High school graduation here. And 6 years of schooling is college graduation. Typical college graduation, and more than that, master level. Anyhow, it's a hard to, like, in this case, scatter plot does not help that much because there are too many observations and they are overlapping too much. So visually it's nearly impossible to tell how many observations are here. How many observations are here? How many observations are here? So reading the graph is not ideal. Instead, the trend line regression model is really nice, capturing the trend. Of course, it's limited to a linear trend, but still it's much better to see what's going on there. And, it's graph. And if you look at the estimators, read this. So the intercept is estimated to be minus 1.965, and education is 0.7431. So that means if you have one additional year of education schooling, then your wage will increase by 0.743. But if you do not receive any education, your wage is going to be minus 1.96 something. So, very strange result, but that's the result. And standard errors are given here. Standard errors correspond to the coefficients. And we have also 95% are given as default, and 99% is at our request. We also obtain 99%, right? So from this, by the way, these guys can be calculated from those values. With simply, you don't need to know them. If you know these, you can calculate them. Let me do this. Simply, the returns to education was estimated to be 0.743, and its standard error is about 0.046, right? Interpretation is when you have additional education, your hourly wage increases by $0.743. Then what is the 95% interval for beta 1 using only these numbers? Without looking at the result table from Excel, what is the confidence interval of 95% level? 3, 2, 1. So first, you have to use 1.96 because 5% error probability must be split half and half, 2.5% each on each side. So you have to use 1.96. 1.96 is the top 2.5% value. And using 1.96 times standard error is the margin of error. So the margin of error is 1.96 times 0.046. So if you use these values and add and subtract the margin of error to the point estimator, beta 1 hat, then you get these numbers, right? Compare that to this guy. So there is 654,833. 654,833. I think the difference is the rounding error, right? Rounding error here or here or here. I'm not sure, but rounding error may occur. And now let's think about hypothesis testing. We have the standard error and point estimator again. Calculate the t-statistic for this hypothesis testing and determine if it is rejected at 5%. 3, 2, 1. So t-statistic is the standardized difference between what you observe, what you get from the data, and what you believe. So their difference is 0.743, easy. And you have to standardize this guy by its standard error, 0.046. So if you divide this over this, you get 16 point something. And 16 point something is huge. This is huge. So any of this threshold is smaller than 16. So H is always rejected at any of these threshold. So the answer is C. Right? So the threshold is 1.96 because we considered 5%, but does not matter. It's well above the threshold. So the determination was easy. Decision was easy. And that's how we calculated this. So this means we rejected the null hypothesis that beta 1 equals to 0. So beta 1 is not 0, which means education is relevant to wage determination. Education is a factor or determinant of wage. So we say education is statistically significant. Its coefficient is statistically significant, or like beta 1 is statistically significant, right? Which is a good news because our model prediction of wage using education is doing something. Is doing something, and it is not useless. And p-value, if you want to calculate the p-value, you have to calculate probability smaller than minus 16 plus and greater than plus 16, which is 0, easily 0. plus minus 16 is really huge outside numbers. And compare the t-statistic and p-value. P-value is 10 to the exponent of minus 56. You have to put 0.0000050 more than 50 times. And t-stat is 16 point something, which is the same and up to rounding errors. Right? Yeah, I'm comparing this here. Okay. The rounding error and another difference here is Excel uses t-distribution as the default, and I explained the difference between t-distribution and normal approximation in an earlier chapter. But in the end, the conclusion is the difference is really small, as you just saw. So my calculation is using normal distribution, but it's nearly negligible. So you don't need to be worried about what is the t-distribution in the end. Especially we have, in this case, the sample size is 2000, more than 2200. So then you don't need a t-distribution at all. T-distribution nearly equals to the normal distribution, I believe. So the difference is mainly coming from the rounding error, not coming from this difference, I'm sure, right? But anyhow, if you can just simply assume that it is a rounding error, and because sample size is large, normal distribution is accurate enough. Approximately, the approximation is accurate enough, so you don't need to worry about t-distribution. Then this is slightly different. Now you believe the returns to education is 0.7 or lower, but you'd like to test it. This is the null hypothesis. Now it is one-sided hypothesis, and it is about 0.7. Belief is at 0.7. Then in this case, using the observations, using the estimation results, calculate the p-value. These two numbers are everything you need to know to calculate the p-value. 3, 2, 1. To calculate the p-value, you first need to calculate the t-statistic, which is the difference, again, standardized difference between your observation, what you observe from the data, and what you believe. Their difference is 0.043. You standardize that using the standard error. So divide the difference by 0.046, like this. Right? Difference divided by standard error is about 0.93. And our hypothesis is one-tailed, and in particular we are looking for upper tail. We're looking at the upper tail, so we reject only when beta 1 is too large, too much larger than 0.7. So our p-value is going only on that tail. So p-value is probability greater than the t-statistic, not the other side. Lower tail is not considered. It's only about upper tail. So p-value is about 17.6%. So H0 is not rejected, which means the returns to education is 0.7, as you believed. But now in this case, we don't say like significance at all. So it's not about significance. Significance is used, like the term statistical significance is used when your hypothesis is about 0. Also, when you reject or when you cannot reject, when the hypothesis that the parameter is equals to 0, then you use whether it is statistically significant or not. Okay, and what you can see from here is only from these two numbers, you can do anything, right? You can test any kind of hypothesis, right? You can test any kind of hypothesis, and you can calculate confidence interval of your confidence level and the standard error is given, point estimator is given. So our theory holds seamlessly, like everything holds in the same way. Even easier because now I don't ask you to calculate anything, right? A little simple calculation like this. This is not algebra. So this is it for now. And in this lecture, I introduced what's the regression model, and it's super important. I tried to motivate the importance of the regression model. I gave you some examples, and then I showed you how to implement regression estimation on Excel. And then I applied estimation theory and hypothesis testing theory using the estimation results. And it must be simple if you have followed all the previous chapters well. But if you have missed some of the previous chapters, then it will be totally new world without knowing anything. So go back to the previous chapters if you are not familiar with any of the previous concepts. Okay, thank you for listening. Thank you for watching. And in the last lecture, the next lecture is the last one. So I look forward to that. In the last lecture, I'm going to show you how we predict and how we can investigate the error terms and how we can estimate. The estimation is actually coming from the errors. So that will be also very interesting and very important, of course. So please, yeah, we'll see you in the next lecture. See you later. Bye.